Sophie is a PhD student at CWI. She earned her bachelor's and master's degrees from Utrecht University. Her research focuses on algorithms for linear programming, in particular using mathematical tools from probability and geometry. And today she's going to be explaining to us why we can solve integer linear programs. So take it away, Sophie.
Thanks, Mary. Yes, hello everyone and welcome. I would like to start by thanking today's organizers for arranging this workshop as well as for the opportunity to speak. So yeah, today I'm gonna tell you about some of the mysteries surrounding integer linear programming solvers and what's been done to address some of the questions related to these algorithms. So my first story for you is about the simplex method for solving linear programs. And my second story is about branch and bound for solving integer programs. A linear program is any problem that can be written in this form right here. And an integer program is any problem that fits this mold down below. For both, you get to specify the matrix A and vectors B and C. And the two problems differ in whether the variables are constrained to take only integer values or not. Now, the task here is to find a solution that satisfies all of the constraints and has the best possible objective value. Furthermore, we would like a proof that the solution we find is in fact good, that has good objective value. So if you're out and about in the world and you find a problem that fits in one of these forms, then modern like off-the-shelf software will give you a good solution to your problem. And the simplex method and branch and bound really are the bread and butter of today's commercial and academic solvers. When it comes to solving integer programs, these two algorithms are actually used together to great effect. So let's talk about the simplex method first. Without going like too far into the details, we can think of the simplex method as operating on this polyhedron that is described as the intersection of a number of half spaces. And we start out knowing a single vertex of this polyhedron. The simplex method will, in every iteration, pivot along an edge to a neighboring vertex in such a way as to improve the objective function in every iteration. And eventually, it will reach an optimal solution to the problem. So in the picture, the objective might be to reach as high up as possible. And if we start here, then in red, we can see one valid simplex path. And different like variants of the simplex method will select different paths to follow. But today we won't really like consider these different variants. But what is important here is that like in practice, this algorithm is blazingly fast. If your polyhedron lives in Rn and it is the intersection of m half spaces, then the simplex method will take at most 3 times n plus m iterations to find an optimal solution. So this is only a linear number of iterations, you might say. And this is where the mystery comes in, because as it turns out, there is this rich literature out there of these artificially constructed linear programs on which the simplex method will actually take exponential time to finish. What's worse is that calculating the output of the simplex method is even p-space complete. So somehow, although hard inputs for the simplex method exist, they never show up in practice. And to like address this mystery, in 2001, Spielman and Tang came up with an interesting way to make rigorous the claim that nearly all linear programs are easy. What they noticed is that the hard instances were all very fragile to change. If you make just a very small perturbation to a hard instance, it suddenly becomes very simple to solve for a simplex method. To formalize this notion, they studied the running time of the simplex algorithm after adding a small amount of independent standard Gaussian distributed noise to any fixed linear program. So Spielman and Tang, they proved a polynomial running time bound on the like polynomial in the number of variables, the number of constraints, and the inverse of the standard deviation of the noise. What this basically means is the more noise you add, the easier the problem becomes to solve. And this original paper of them was like 90 pages long, and it was very complicated. But improvements and simplifications due to first Verschinnen and later myself and Daniel de Douche have actually made great strides to get a more reasonable bound using a shorter and more understandable proof. So inspired by this work, we are now working with a group of people to study what's known as the combinatorial diameter of random polyhedra. So this combinatorial diameter, it's a number we can associate to any fixed polyhedron, and which in a sense measures the running time of the smartest possible simplex method. And what we proved is an upper bound, like the first upper bound on the combinatorial diameter, specifically for random polyhedra. And what I think is like really interesting about this is that the upper bounds we got are much stronger than the worst case lower bounds. So we have this sort of similar thing going on where the average case is much easier than the worst case. And our smooth analysis results from the previous slide, it was actually used this year by Narayanan, Shah, and Srivastava to prove something close to an upper bound on the combinatorial diameter in the smooth analysis model. And I think improving this to an actual upper bound on the combinatorial diameter is a very interesting open problem. Now, let's turn to integer programming, which is in fact the more difficult of the two problems we're considering today. So integer programming is in fact NP complete. Today I want to focus on the formulation here on the slide, where all the variables we assume take value either 0 or 1. And if you want to solve any problem that fits this mold, your workhorse algorithm really is branch and bound. And again, on a sort of high level, this algorithm works by branching on different choices, such as variable I takes value 0 or variable I takes value 1. This will, like in this way, the algorithm will build a tree of possible choices, and the algorithm will cleverly choose which leaf of the tree to process next to branch on further. So what we're interested in here is the size of the tree that is generated. Maybe like interesting is as a very quick aside, the two researchers who invented this very important algorithm actually published their paper under only their initials. Turns out that they did this to be taken seriously because they were in fact two women. They were they were Alison Land and Ilsa Doig. Maybe nice to know is that Alison Land, when she passed away earlier this year, The Guardian actually published a really nice obituary about her work in like operations research, where she was quite well known. But yeah, back to our story. So we have this branch and bound algorithm, which can solve many problems in a reasonable time, even though some simple inputs have it generate a tree of exponential size. And here we see one example. If we want to maximize the sum of our variables, subject to the same sum being at most n over 2, well, we can eyeball this value. The optimum value to this problem will be n over 2 rounded down. But if you would use a branch and bound algorithm to try and prove this, it would actually generate a tree of size at least 2 to the n over 2. So this algorithm is really slow on even this very simple input. So we have a similar mystery going on here. Hard inputs exist, but in practice, we don't see them so often. And this year, we saw a real breakthrough happening in the analysis of this branch and bound algorithm. where Day, Dubé, and Molinaro proved that if you have a random backing integer program, that is an integer program where the matrix A and vector C have independent entries uniformly chosen in the interval between 0 and 1, then branch and bound takes time polynomial in the number of variables with good probability. The degree of this polynomial does grow exponentially in the number of constraints, however. But what is, I think, most interesting about this result is the way in which they prove this. So we have this way of measuring how well an integer program is approximated by its so-called LP relaxation. And this proof of Day, Dubé, and Molinaro shows that if the approximation is better, then the running time of the algorithm is in fact lower, which really does confirm what we see happening in practice. So naturally, when we saw this paper, we got really excited about it. But we thought, well, all these input data, this A and this C being all positive numbers, is a bit too restrictive. So what we did is we extended their result to the case where this C and this A have independent standard Gaussian distributed entries, and where this B vector is not too negative. And what we found is that we in fact got a much stronger running time bound, where now the exponents only grows polynomially in the number of constraints. I think there's a large number of interesting ways to like take this line of research, to look at like different distributions or to assume some combinatorial structure. Mostly due to the fact that like your real life problems don't look like they come from a Gaussian distribution. So it's would be nice to like have some more scope in here. If you would like to learn more about analyzing algorithms beyond their worst case performance, I recommend checking out this new book that came out last year. Actually, it was edited by Tim Roughgarden and contains more applications of smooth analysis, which we saw today, as well as different methods of analyzing algorithms. And in fact, myself and Daniel wrote one chapter on this book about the simplex method, discussing both the result I mentioned as well as some others. Thanks all for your attention.